Hey everybody, welcome back. I hope you're all doing well. It's the weekend and I have a little bit of time for a quick project here. So we have a Yamaha model CR-400 receiver, and I don't know very much about it because I got it a while ago and I don't even remember what, if anything, is wrong with it. So I think the first thing we're going to do is just kind of do an assessment, see if it works, and if it doesn't, we see what doesn't work, and then we'll decide what we're going to do with this project from there. Now, this is the first of two Yamaha receivers that I have. The other one that I have is a larger model, and it definitely has issues and will need to be troubleshot and repaired. But we're going to save that one for a little bit later because I don't really have the time to get into a bigger project like that right now. So let's take a look at this and let's see where we go with it. Okay, you're going to have to kind of forgive all the fan noises in the background. If you notice, sometimes when I'm doing a video, you hear a lot of background noise, and then other times it's really quiet and the sound quality is really good. Part of that is because I'm down here in the basement. I have a basement shop, and our furnace is not very far away from where the bench is. So when the furnace kicks on, especially on a cold day like now, you get all that noise. So sorry about that, but it's the best we got. And then when it kicks off, it'll get nice and quiet and you can hear me better. Of course, I don't know if that's a good thing if you really want to hear me. Anyway, I have this plugged into the the dim bulb module over there, and I have the smallest bulb turned on. It's only a 40 watt. And I just want to see, when I turn this on, if there's any shorts or anything. We're just going to try it right out here. And we're going to turn this on. And even the 40 watt bulb doesn't light up at all. The bulb isn't even glowing. So there's extremely low current. That's a good sign because that means that at least we don't have any shorts. Now, these lower end receivers, a lot of them do not have speaker protection. So if your output transistors are shorted, you may not get heavy current on your dim bulb. And when you go to connect a set of speakers to it, you will have an offset voltage on there and it will damage your speakers. So you saw an example of that on a Kenwood, I think the CR-400 receiver that I did a repair on earlier. We don't want that to happen. So the next thing we're going to do is we're going to turn this around with the power, and we're going to turn the power on, and we're just going to check the speaker terminals to see if there's any DC offset. Okay, the receiver is still powered up, and I've just turned it around. And we're going to set this to DC voltage, and I have speaker A selected on the front panel for the speaker selects. Now again, we don't know if this receiver, without looking at the schematic, we don't really know whether it has a speaker protect relay or not. But again, a lot of these smaller receivers will not have that. So that's why we're going to check it. So we're going to check a few things before we even take anything apart to see if we can maybe see if it makes sound. Okay, so there's just 65 millivolts of offset on that channel, on the right channel, and on the left channel 45 millivolts. So that's a good thing, because if there was absolute 0 volts, that means there would be, because there's almost never no offset, there's always a few millivolts. So the fact that there's a few millivolts means that the transistors are at least somewhat biased, and there are no shorts that we can see, at least in the output section. So at least it tells us it's safe to connect some speakers and test everything out and see if we can get any sound. So let me connect some speakers and I'll be right back. Okay, speakers are connected. And I have sound out of both speakers. All right, let's connect an antenna and see if we can get some stations. Okay, let's turn on once again. Now we have an antenna. Right away.
Premature. I mean, there is no denying
Wow. Well, I would have to say that just by that little tiny bit of dial scan, we do not have to do anything to the tuner, and the amplifier sounds okay so far. We can put a little bit of music into the auxiliary and see how that works out. So let's try that. Okay, we're switched over to auxiliary. Turn up some volume. Let's start a song. And there is absolutely nothing. And there is absolutely nothing there now, too. Now there's no sound. How about that? Let's turn it off. Go back to FM, because we know it worked there. Turn it back on. I don't hear the speakers thumping or anything anymore. The amp's dead. So there you have it. It worked for a minute and it stopped. Now obviously we still have tuner action here because we can still tune, but there is absolutely no sound. Nothing. Interesting. All right, well, I guess, and there doesn't seem to be, let's take a look here. That's an interesting problem, isn't it? And let's look and see if we get any voltage here on our speaker terminals, although I don't hear anything. It's gone completely, pretty much dead on both channels. So whatever it is, it completely shut everything down. So I think we're going to need to get a schematic up here and see what's going on. So what do we know so far about this? Well, first of all, we know that when we first turned it on, it worked for a while and everything seemed to be okay. Then after it was on for a little bit, it shut off, or the sound cut out. Now, the first thing we want to remember is that both channels went out, and it appears as though we still have at least part of our power supplies because the tuner was still working. Now, another thing we can try is we can try to see if we get something out of the preamp outputs on this, because this one actually has, I believe, a preamp output. Let's see here. And you can see right there is a pre-out. I don't know if you can see that or not. There it is. Right here. So I think the next thing we're going to do is we're just going to connect that pre-out to the oscilloscope, and we're going to see if there's any kind of sound coming out of the preamp, and that'll narrow us down to the main power amplifier section. And we could have done this without taking the covers off, but obviously we know there's going to be something wrong in here, so we're going to have to take the covers off anyway. But let's do that. Alright, I just connected a set of RCA jacks, or connectors, to the pre-out. I've turned the amplifier on. We're still on the dim bulb, and I've connected it to the two channels of my oscilloscope. Now I'm set to FM, so we'll just get some static because I disconnected the antenna. But when I turn the volume up, we should, and we do. And you can see as I turn the volume all the way up, all the way down, So there is definitely sound on the preamp. So that would lead us to believe that the problem has to do with the power going to the power amplifier. Now we don't know how this power supply is designed, so now we have to get out our schematic and we need to look and see what the power supply is, how it's designed and what could possibly fail in it to cause this kind of an issue. Because I really believe this is going to be a power supply related problem, at least for now, because both channels went out at the same time. Okay, I have a new camera mount, or a new monitor mount arm for my computer monitor that makes it a lot easier to see the schematics now and to get the camera zoomed in on it. So that's nice because I don't have to print out a bunch of papers anymore. And let me put my computer seeing glasses on. Yeah, I have with the progressive lenses, sometimes the normal ones are a little difficult to see things up close like this at this angle. So I have special glasses for that. Again, thank you to the viewer who recommended this. I will be in forever gratitude to you for this. All right, so if we look here, let's do something fun. Let's use our lightsaber pointer today. And right away, I can see the preamp out, and that comes straight out of here. So all of this is working. We must have power to this section over here. Here's your power amp section, and we're zoomed in quite a bit. And here's our power supply. So looking at the power supply, you have 1, 2, 3 different windings on there, and we actually have another one that's not even being used. And that might be for rewiring this thing for different countries for different voltages. So we know we got power going into the transformer. We know that the transformer is putting some power out. We have 20 volts AC on either side of this winding here with the center tap. We have 28.8 volts right here, which I'm going to probably say is going to go to our low voltage regulated supply for the tuner and so forth. And then you have this other winding, which is probably going to the preamp or something like that, or vice versa. So we have 2 lower voltage power supplies. This one says 11 volts. This is 28.8. And then these are 220 volts. And that's probably what's going to give us our plus and minus for our push-pull output. So my guess is the problem is going to be somewhere in here. If we drag this down and look at our power supply section, let's see if I can get it all on there. And I will move you in so we can zoom a little bit. Can't zoom in too much or you won't see the whole thing, but pretty close. Okay, so these windings all come up here and they go onto the power supply board, and the first thing we see is a bunch of fuses. We have F701, 702, and 703, and then we have a couple of little pico fuses. They're 4 ohm and they're designed to open up 300 milliamps. And real quick, a little fact about fuses. Just because a fuse is rated at 2 amps, that doesn't mean it's going to blow at 2 amps. As a matter of fact, it will never blow at 2 amps, unless it depends also about the voltage. Remember that a fuse is a piece of wire, and a piece of wire has resistance. Ohm's law still comes into play. The current is only part of the equation. When you look at what that filament can handle, it's not handling current, nor is it handling voltage. It's handling current and voltage, or it's handling wattage. So even though you're drawing 2 amps through a fuse, if you're drawing 2 amps at 1 volt, you're putting a lot less heat into that filament of that fuse than if you're drawing 2 amps at 250 volts. So this is where people get caught up a lot. They say, well, these are defective fuses. There's 2 amps. Well, I got news for you. At lower voltages, these will go a lot higher in current before they blow. And if you notice, automotive fuses, the glass ones that are the the same 7 millimeter or the 1/4 inch fuses that you're used to seeing. If you look at the side of them, they're rated at 32 volts at that amperage, not 250, and there is a difference. They will blow at different current rate, wattage ratings. So I always thought that fuses were very interesting, how they're rated, at voltage and current. But you really, in some ways, they should rate them by the wattage. So anyway, that's enough about fuses for now. Let's check that, because what is the first rule of electronics? Thou shalt check thine power supplies first. So that's what we're going to do. And normally what you would do is check the fuses before you do any schematic work or anything. But I want to go through this process with you. So let's go down and let's check our fuses. Okay, making sure the power is disconnected from this thing. We're going to go into ohms. And let's see if we can get this at an angle where we can see. And of course now the camera's right where I want to be. So here is the first fuse. This is, what does it say? I can't even read it because it's all covered up with the sticker. But this is one of the fuses. Look at that. That fuse is shorted out. All right, I'm kidding. We actually had a bench tech that said that one time. Came to us with the fuse and said, I think I found the problem. This fuse is shorted. Well, you want to laugh, but you know what? This is how people learn, So let's check this other one. Okay, that fuse is good. That one is not good. 480,000 ohms, 480K. That fuse is open. All right, so that's problem number one. This little pico fuse here is supposed to be 4.3 ohms, and if I can really get my meter on it, maybe it actually will be. I don't know. Yep, 4 ohms. How about this other one? 4 ohms. Okay, so this fuse here is bad. And we will need to find out why. So this is 250 volts, 500 milliamps. And you can see it's well, that looks like crud on the outside of the fuse. So it doesn't look like it's obliterated. It just looks like it opened, but it doesn't look majorly exploded. So that means there's not a dead short, and that makes sense because it worked for a little while. Now this fuse does not appear to have been replaced anytime recently. So that's kind of strange. And again, I don't remember when I got this amplifier, this receiver, I don't remember what the problem was with it. But obviously something was going bad, and it looks like it went the rest of the way bad while we were sitting here playing with it on the bench. So let's look and see if we can find out which fuse that is and why it failed. Okay, zooming you down on here, we can see that this is the 500 milliamp fuse. The other two are 2 amp fuses. So we want to go up to the schematic and find the 500 milliamp or the 0.5 amp fuse. Let me go up here and put you back on the camera, or on the monitor here. And if we look, that is this fuse right here. And we have a 10 ohm current limiting resistor, and this goes to ground. So this is actually the fuse going to ground. And if we follow this down and we go over to here, this is the second one over, it goes right to the center tap of the plus and minus for the output section of the amplifier. Now, what does that mean? Well, if you look, the 2 power fuses that provide the power to the amplifiers, Those are 2 amp fuses. The center tap that they refer to is actually connected to a 1/2 amp fuse. So they're not expecting more than a 1/2 amp of current draw, at least to that center tap. Okay, so there's a couple things that we want to look at here. The first thing we're going to do is see if it's just a power supply. Normally when a transistor starts to leak like that under temperature, what will happen is you'll see problems with DC offset. Now on a higher end amp, that DC offset will actually trip the protect relay, but this one can't do that. And that's one of the reasons they have that little fuse in there. That's the only protection you have for your speakers if something starts to short out. However, if part of the power supply shorts out, that may not do that on the power amp, and well, at that point in time, it might just be that we have a capacitor or something that's beginning to leak, or high ESR or something like that. So we're going to look at that. But being how quiet this amplifier was, that may not be it either. So we're just going to divide and conquer. So the first thing we're going to do, we're going to check the capacitors for ESR, and we'll just do a very rudimentary leakage test. The other thing we're going to do is, if we don't find any problems there, we're going to disconnect if we can, if at all possible. We're going to try to isolate the 2 amplifiers, and we may be able to do that by just pulling one of those 2 amp fuses, because I think one fuse goes to one channel, the other fuse goes to the other channel, and we may be able to disconnect power from one channel and see if the problem goes away. The other thing I noticed is the cat in heat has been here. This thing, these controls are completely embalmed with oil, with that spray, whatever. Yuck. I hate that, because now I have to clean that all off. If you touch it, it gets all over your fingers and everything. All right, enough of my rant about that. Everybody gets all upset over that, so we're not going to talk about it. But so it's just all over the pots and the controls. Okay, so somebody did try to service this, but I think when this problem here happened, I don't see any signs of any of these components being, well, yeah, I do. I'm seeing something. Okay, hold on. Okay, looking in through these little access holes, it appears as though somebody did some really bad soldering and trashed the tracks here on this board. So it looks as though they've attempted to either replace or remove and test these output transistors, and had a little bit of problem with it. So yeah, apparently this must have had an intermittent problem. Somebody went in there with a can of spray and sprayed the controls, and then when it didn't fix it, they sprayed it more, and when it didn't fix it, then they went on Google and read that the outputs go bad, so they tried to remove the outputs, and that didn't fix it, and I think that's when it went up for sale. I'm guessing that scenario. It could be something totally different than that. Okay, we're going to check these power capacitors first, and that's got real low ESR. And when you test this with this meter, if it goes all the way to 0, that is an indication that the capacitor could possibly be shorted, or there is a very low impedance across, shunted across that capacitor. If you have just a little bit, less than 1/10 of an ohm, but it's above 0, so it's right on 0. But if I go here, it's not 0. It's about 50 milliohms. Same thing with this one. So chances are the capacitor is not shorted. It could be leaky. We don't know. We would have to do a leakage test. But it does not have high ESR. So you're not going to get crazy ripple, and you're not going to cause overcurrent because of the capacitor, unless it's leaky. I doubt that it is, though. I think our problem is going to be in the transistors. I think, again, there's most likely a driver or pre-driver transistor that's failing when it heats up. And I think, they went for the outputs and maybe just didn't check the drivers, because I don't see any indication that any of the drivers were tested. So that's where we're going to go next. Okay, these two SC1061s and two SA671s, their pinout is base, collector, emitter. So if we're looking from the other sides, we're upside down, but it's base, collector, emitter from left to right. So that's how we're going to check these out. Now we're going to be reading across other circuitry, so this isn't going to be perfect. Now remember, this is an NPN. This one is a PNP. So the NPN, that means the P lead, or the red lead for this meter, will be on the base. So if I go from base to collector, I see a diode drop. If I go from base to emitter, I see a diode drop. If I go from emitter to collector, that's fine. And again, you can't really check leakage with these because you're not really applying any current. Now this one is a 2SA, so we have to reverse it. And this one, the base is going to have the N on it. And we're going to check again. And you can see right there, you're reading across a capacitor. When it settles, we should see about that half a volt drop, and that we do. And we go from base to emitter, and that's kind of low, but again, I think we're reading across something. We're going to compare it to the other channel. Alright, let's go to this one. This is the NPN again. Good. It reads just the same as the other channel, or not. How's that? That's not good. So right there's a problem, possibly. That might not be. There's 4 transistors, or 5 transistors in here. I'm not sure what that 5th one is. It must have something to do with the voltage regulator or a power supply. But let's look at this outside one and see if it matches this one. This might be for a power supply. Okay. Okay, so good. Nope, same thing. So we definitely have differences between the two channels right there, indicating that either our output transistors are bad or something connected to them is bad. So there's your first problem. So we are going to have to pull these out to properly test them, because you really can't test that in circuit. Okay, looking at the layout of this and looking at the board layout and the schematic, this transistor here is TR-702, and it is the current pass transistor for the power supply. That's why it read different than the other ones. These two are for the left channel outputs, and these two are for the right channel outputs. So that makes sense. So these may not be bad after all. So I'm not going to remove them yet. What I am going to do is I am going to put a current meter in here, and I am going to remove power from one of the channels. We're just going to pick one randomly and we're going to see if that causes the fuse to blow. And then if it doesn't, we're going to go to the other channel and try the whole process again. Okay, you know what they say, you can never have too many meters. So here's my setup. I still have this connected to the current limiting bulb. I have 3 meters. The Fluke 187 is connected to the bias test points on the left channel. The Fluke 27 is connected to the bias test points on the right channel. And this amp probe meter is connected right across the fuse socket of that fuse that blew out. And remember, that is a 500 milliamp fuse, so it should be less than 500 milliamps there. Now, this is a 400 milliamp fused socket when it's on the milliamp scale. And so we're going to have to monitor this, but the reason I'm doing this is the fuse in this meter is a lot cheaper to replace than the fuse in these meters if it opens up. So anyway, we're going to monitor this. I have a 1 kilohertz sine wave signal feeding into the auxiliary inputs, and we do have a dummy load connected to the speaker terminals so that it will simulate driving a set of speakers. And we're just going to turn the volume up. We're going to watch the bulb light up over there. We're going to look at what the bias voltage does. Don't worry about this right now because the bias voltage is supposed to be about 25 millivolts. If you notice, it's pretty low on both channels. And the reason for that is because we have that tiny little current limiting bulb in there. That is the smallest of the 3 bulbs. It's only a 40 watt. So our voltages in here are much lower than they normally would be, so your bias is going to be low. Won't hurt anything, we can still run the circuit. So if I turn up the volume, we should see our bias voltage go up as the circuit begins to function. We can see we're really not getting any current, very little current, less than a milliamp to that return point of the. If we look here, that's DC milliamps and AC milliamps. And remember, this is the center tap of the power transformer for the winding for the output section. So most of the current is flowing between the positive voltage and the negative voltage right now, and not through ground or through that center tap. So we're just going to keep monitoring this, and you can see everything's behaving pretty well so far. If I go up here, everything's still working. So I'm just going to play with this for a little while. I'm going to leave the camera run, but I'm going to probably edit out all the boring sitting here watching it parts. And if something happens, I'll make sure I come back and we'll leave that in the video. Okay, I have been running this for quite some time right now, over half an hour. I've had no problems with it. So I started kind of checking some things, and heatsink is warm now because I have been putting some signal through it. So I went through and I just started feeling some of these components here. And when I got to this capacitor, it's running pretty warm. This one is a little bit warm. It's lukewarm. Ice cold, room temperature, and above room temperature, but not too warm. So these 3 right here seem to be running, and they are all the same type of capacitor too. And usually when a capacitor gets warm like that, it's usually an indication that the ESR has gone up in them. They have high ESR, or that they need to be reformed. So what does that tell us? Well, if this doesn't fail, if this keeps working fine, my guess is that this amp has been sitting for a while, that whoever replaced the transistors in this or whatever they did fixed it, and that just these capacitors, since they have never been replaced, they just needed to reform. And because they were leaky when we first powered it up, it caused excessive current in that center tap, which obviously caused the fuse to open up. Now normally there should be almost no current flowing through that center tap like this, the AC there. And the reason being is that most of the current is flowing between the two outer, well, let's take a look up here. So when we look at this power supply, you have these three leads coming off of this winding. Center tap goes through this 10 ohm, it's kind of like a current limiting resistor, and then from there it finds its way to ground. This is all common to the chassis and to this negative terminal of the speaker terminals. But here's your positive power supply voltage and your negative power supply voltage, and really the current path is this way through these two capacitors like this. Normally, because it's a push-pull circuit, what will happen is as one turns on more, the other will turn off more. So there's always going to be a balance, and as a result, this center point here is going to be, you know, pretty much a net zero with respect to right here. So there really shouldn't be a whole lot of current flowing through here unless one side becomes imbalanced from the other. At that point, then you will see current flow through that center tap, and that's what this is in here for. So when the machine's first powering up, when there is some sort of a a transient or something, you can have little current spikes there, which won't hurt this fuse. But if you have a serious imbalance, like one channel, one transistor on one side shorts out or something, what's going to happen is it's going to cause an imbalance and it'll open that fuse. And I think that's what happened when one of those capacitors was forming. When it was starting to reform, it pulled down one side, either the positive side or the negative side, and caused excessive current at the center tap and opened the fuse. So this is an interesting problem. Now, there still could be a failed component in here, and it just hasn't reared its ugly head yet. But being that this only happened one time, and being that we can't get it to repeat itself, and that those capacitors are warm to the touch, my guess is that we had capacitors reforming, and that's what caused that fuse to open up. But we're going to keep testing it for a while, and if anything changes, I'll come back and I'll let you know. Okay, looking at the schematic, we have this one, and this one, and all three of them are 100 microfarad at 50 volts. This one has since cooled way down. It's like room temperature. This one has cooled down for the most part. This one is still warm. Not as much as it was, but it's still a little bit warm. Now, where do those exist on the schematic? That's our big question, huh? So let's zoom in a little bit, and let's bring this into where you can see it. So that first one, the one that was on the far left, is right here, and it's actually part of the power supply, and it is not related to that center tap in any way. This is on a different winding and everything, so this could not have caused that fuse to blow. However, if we look at these two down here, there's one of them right here for the left channel and one for the right channel. Okay, and looking at that right here, see it? That goes straight over to here, and if you follow the wire up, straight up here, this outer wire goes to that center tap of the transformer right there. And if you look at the other end of the capacitor, it's connected to your rail voltage of, there should be, right here it says negative 23.6 volts. Or I'm sorry, negative 26 volts. See it right there, 26 negative. And then there's also negative 26 on the other channel as well. So you have 26 volts across that 50 volt cap, which is normal. But if that capacitor had very high ESR, I could see how that would cause current to flow through that center tap, pop that fuse. And that's where I think our problem is right now. So I think the caps have mostly reformed except for that one, and I think they'll be okay for the time being, but that's usually not something for the couple dollars of parts it would cost that I would leave alone. So what I'm going to do is I'm going to replace just those few capacitors in there. I'm going to leave all the rest of them in place because they all seem to be okay. They're not having any problems. And I think this amp's going to work. I don't think we're going to have to do anything else to it. Okay, here are the two caps that got warm. And they look fairly okay. Not too bad. Here, focus. And here's the one that stayed warm. Notice any difference? Look on this pin right here. Yeah, it leaked. So there you go. Bad capacitor. I'm sure we can put it on testers and stuff. I don't really care about that. It's bad. So we're going to replace it. I may look at the other one simply because it has that glue all over it. These ones didn't have glue on them. The bigger ones do. And those tend to corrode the leads sometimes. Some of the glue does. Not all the glue does, but certain types of that glue they use to hold the caps down when they solder them in will do that. I'm going to replace with these 100 microfarad 50 volt caps, and they're good for 125 degrees Fahrenheit. They are very heavy duty. They are designed for industrial, so they're not going to go bad. They're low ESR. They're good caps. So replace those. We'll never have to deal with that again, and at least not as long as I'm around. And I think this thing should be ready for the races. Okay, the new capacitors are in. I did replace that 470 just because I was in there. I think all the others are good. And the proof is in the pudding, huh? We're going to have to listen to it and decide whether everything else is okay or not. And we're going to go on millivolts with our meter. And let me get everything in view. Alright. Let's turn this on, and what I'm going to do is, as long as this powers up and everything's okay, I am going to go ahead and put full power to it. But before I do that, let me go get a fuse and put in there. I forgot to replace the fuse. Well, the fuse is replaced, but while I was in there in my box of fuses, I found this laying in there. Now, some of you, probably none of you know what that is, but if any of you know what this is from, what a polytome is, let me know down in the description. I'll give you a hint. It was featured in a movie. It was actually a device. It was a real thing, but polytome. Okay. Let's turn this on and let's see if our fuse stays intact. So far, so good. Okay, so this is coming up okay. I'm going to go to direct now. Take it out of current limit mode. I'm going to wait for this to stabilize a little while, and then I'm going to go ahead and set the bias because we want about 25 millivolts in there, although it probably doesn't have to be that high. They always leave a little bit of leeway in there, but we'll set it maybe a little closer to 20 millivolts of idle current. If it's too low, you'll get crossover distortion. If it's too high, it'll make the amplifier idle at much higher temperatures. So Well, let me give it about 10 minutes to warm up, and then I'll be right back. And this is why you leave it warm up for 10 minutes or so. You can see the bias is creeping up a little bit as the amp warms up, and that's normal. But we're going to have somewhere near that 25 or 20 to 25 millivolts. It's kind of stabilizing around there right now. Let's go over to the other channel and see what it's sitting at. That one's a little bit low. So that one we can turn up a little bit. Again, this isn't super critical. People try to split hairs with, tenth of a millivolt, and it really doesn't matter. Get it within that range, it'll be fine. If you get a little bit of crossover distortion, you know it needs to be turned up a wee little bit. And if you have it a little below the recommendation and you're not getting any distortion at low volume levels, leave it, because it's just going to allow the amplifier to dissipate less energy when it's sitting idle. So, I'll probably have this sitting somewhere around 20 millivolts. And we'll go back over to this one, check it, and we'll go back a couple of times and just make sure it's still holding. It's right there on 20. Go look at this one. It's sitting close to 20, so that's good. We just wanted to make sure that was where it needs to be. Let's hook up some speakers and see if we can play our song that we were trying to play earlier. Okay, bonus footage. All of the panel lamps are burned out on this. So the dial indicator lamp and the 3 meter lamps are bad, so we're going to have to replace them. So to get the dial light out, what you have to do is you take this metal trim strip off the top, 2 screws, you gently lift this up and out of the way, and I'm just going to tune it off to the side here so I can get to it. I'm going to put my new bulb in. The old bulb was just kind of laying in there like this. See how it's folded? So we're going to put the new one in the same way and then route the wires through. And what I'm going to do here is I'm going to, just like they had theirs twisted, I'm going to twist the wire on this one. I'm using LEDs on this one instead of incandescent. You can see how it burns. The incandescent gets hot and discolors and makes the plastic brittle. You can see how this is cracked here already, and this little brass insert could very easily come out if we're not careful. So we're going to be extra cautious with that. And what I am going to do is, just like they have this sleeving on this one, we're going to put it on the new one as well. And I have some here, if I can find it. Let's see. Just use a little piece of heat shrink or something. Something that's pliable and that you can pinch in there. Then I'm going to fold this underneath like so. My cousin had great big ham hands, and I'll tell you what, he could use a little pair of needle nose pliers like nobody's business. It was like an extension of his hand. He never dropped anything. And I don't know. I'm not so talented. Okay. I'll pull this over here. I don't want to bend these leads too hard because these are LED leads and they'll crack if we're not careful enough. I'll put this one in its place like that. And we'll solder those in shortly. Okay, we'll do all the solder connections at once. Put this back here. And then I will remove those other ones, and hopefully they're not, the little grommets aren't all dried out and hardened and breaking. Let's see what we can do. Okay, we're all set. The lights are back in. Nothing that a little bit of solder and heat shrink couldn't fix. And let's turn some lights off here so we don't have so much glare. See what this looks like. Perfect. All right. Good as new. That was it. And I know I didn't go through all the crazy routines of connecting the scope and doing all the distortion analysis and all that. We certainly could do that, but I think you've seen that so many times in so many of my other videos that it's not necessary to go through all that again on this. We'll check the inputs, make sure they all work, although I'm pretty sure they will. Verify that the radio is working, although it sounded really good. And make sure that, again, playing this for a while, the problem doesn't come back. You know, we're assuming that those capacitors were the problem. But you still can have a transistor that can fail. And sometimes they go intermittent, and sometimes, you know, just when you think you have it fixed, it's back on the bench. So nothing takes the place of a good bench test. Let it run for a while. Make sure everything's good before you button it back up. But I think that's it for this video. If anything changes, I'll be back. But if not, again, I wish you all peace, joy, happiness, and good health in your lives. We'll see you all again real soon. And not sure what video I'm going to do next, but have a couple ideas. But anyway, take care, everybody. Stay well, and we'll see you again real soon.